morning, everyone. I do not want to cut into Dr. Turok's time, so I'm going to get started. I first heard Dr. Turok speak at the Canadian Science Policy Conference in Ottawa last year on the topic, We Are Innovators. We are very fortunate and honored to have Dr. Turok speak at our STAO conference. Dr. Neil Turok is the director and Niels Board Chair at the world-renowned Perimeter Institute for Theoretical Physics in Waterloo, Ontario. Previously, he was reader at Imperial, professor of physics at Princeton, and chair of mathematical physics at Cambridge. He is interested in developing and testing fundamental truths of the cosmos. Turok's research focuses on developing and testing cosmological theories. His predictions for the correlations of the polarization and temperature of the cosmic background radiation, CBR, and of the galaxy CBR correlations induced by dark energy have been confirmed at high precision. He has pioneered detailed investigations of many theoretical proposals, including cosmic strings, single bubble inflationary universes, the basis of the multiverse paradigm, as well as cyclic universe scenarios. Born in South Africa, Turok founded the African Institute for Mathematical Sciences, AIMS, which operates centers of excellence for postgraduate training and research in South Africa, Senegal, Ghana, Cameroon, Tanzania, and Rwanda. For his discoveries in his work building AIMS, Turok was awarded the TED Prize in 2008. In 2012, he delivered the CBC Massey Lectures broadcast across Canada and published as The Universe Within, a prize-winning bestseller. In 2016, he was awarded an honorary fellowship of the UK Institute of Physics, the John Torrance Tate Medal of the American Institute of Physics for International Leadership in Physics, as well as the John Wheatley Award from the American Physical Society. On behalf of the executive and board, it is an honor and privilege to present to you Dr. Neil Turok on the topic, Science and Our Future.
I'm a theorist, and I just destroyed the apparatus. It's a real privilege to be with you here today. Mike, thank you. As I said, I'm a theorist. It's a huge privilege to be. Ooh, that's very echoey. Is the sound good at the back? Testing. 1, 2, 3, 4. Can you hear me at the back? Yes? Good. Okay. Thank you. So it's an enormous privilege to be with you here today. I didn't expect this to be quite that big an occasion. I've written a bit of a mishmash of a talk. It includes many things. I'm trying to respond to the situation we all find ourselves in, which is both very troubling and confusing and even threatening. But at the same time, there are all kinds of opportunities too. And as you'll discover from the talk, I'm not a pessimistic sort of guy. I'm a very optimistic individual. And I hope to share some of that enthusiasm with you, and particularly for teachers, because you are on the front line. You are the people who can help young people to get some perspective on what it's all about, what values are, what science offers, how to relate to each other. And these things are more urgent today than ever before. So I'd like to dedicate this talk to Stephen Hawking, who was a good friend of mine, and I was very privileged to know rather well in Cambridge. And he passed away earlier this year. I went to the funeral for him in Cambridge and in London. It was really a very, very moving occasion, very special person who in many senses, is still with us, and he will reappear in this talk in various guises, as you'll see. But I also want to dedicate this to teachers everywhere. Teachers are under threat, under pressure. You know this much better than me. And in my view, this is the worst thing we could possibly do for our future, is fail to support teachers, because teachers are creating the future every day. I took this off the internet last night. It's kind of representative of the times we live in. It's a picture of Times Square, and people saying you can't fire the truth. We're in the midst of a very intense debate about what is the truth. How do you define the truth? Who gets to define the truth? Is it just power or more access to internet, ability to flood the internet with all kinds of false information? And you see the other sign about the law. I'm sorry, it's another sign about the law. These things are very closely related. You know, the origin of the notion of law is very closely allied to the origin of science. They were simultaneous. I'll talk later about mathematical proof. What does it mean to prove something? Well, that notion actually comes from the notion of justice. That if you accuse someone of something, you have to prove it. You can't just make an assertion, right? And just because you're powerful, like some king or despot, expect to be believed. There was a notion developed in ancient times that you have to prove somebody guilty of something, or prove your case. And that's the basis of the law, and it comes along with mathematics and mathematical proof, where you convince yourself something is true beyond any doubt. And so that rigorous way of thinking is under threat today. And this is a huge challenge we all have to face. And the sort of, I mean, it's very symptomatic that this is all taking place. There are all these worried people surrounded by adverts, right, in Times Square, just streaming all this stuff, trying to convince them to buy X, Y, or Z. And this is the powerful technology, information technology, we have created and which now engulfs us, and which we have to screen out. Okay, and we have to be very clear who we are, what we want to do, what our values are, and we're in the midst of coping with this over torrent of information, most of which is worthless. I'm going to talk about a particular teacher, and actually, like many scientists, I steal from other people. That's what we do. We call it sharing. And I stole the title of this talk from Edward Condon, who was a nuclear physicist. And you see, he was a teacher. In fact, he was the teacher of Carl Sagan. You may have heard of Carl Sagan. Edward Condon was a nuclear physicist, therefore was involved in the developments leading up to the nuclear bomb and the Manhattan Project, from which he resigned, incidentally. But just after the Second World War, Edward Condon gave a talk called Science and Our Future, which I have stolen the title of. And his whole message is, how are we going to cope with this power we have to destroy the world? Okay, so here is his lecture. He was the director of the National Bureau of Standards, and then in 1946, he gave this lecture. Actually, it was to young people. It was the winners of the Westinghouse Prize, which is given to the top high school kids in physics. And so he gave this talk, and I just want to show you one quote of it. A couple of quotes actually. We see that man, sorry about the gender bias, we see that man's growing mastery over the forces of nature also serves to amplify the magnitude of the social crises which confront him to be up. But so that was the dilemma. Having created the nuclear bomb, how do we save ourselves from from the danger it poses? And then he says, and this is very naive, idealistic stuff, I beg of you, cast in your lot with persons of the second kind. By the way, persons of the first kind are sort of cynical, and they say, here's a quote from one of them, extravagant expressions of horror will not alter the course of events. So that was some pompous academic, actually an anthropologist. Beginning by quoting. But he says that's the person of the first kind. They basically say, it's all public, whatever happens will happen. Persons of the second kind, those who believe there is a possibility that men, again, people throughout the world can live in freedom and justice, in love and goodwill, that they can devote their full energies to the constructive application of rational thinking, to call science to the arts of peace. Okay, so that was his message. We need to get the whole world on the same page to use science to promote peace. And what happened to this person? Well, he was accused of disloyalty to the United States by the House Un-American Committee. This is the famous McCarthy era. And he was basically called a spy. And he gave evidence at a loyalty panel. At that time, they went around the US interrogating people and saying, are you really loyal to our country? It was the Cold War era. And so the chair of the panel said to him, Dr. Condon, and in another place he calls him Dr. Condon. He said, Dr. Condon, it says here that you've been at the forefront of a revolutionary movement in physics called, and here he read the word slowly and carefully, quantum mechanics. It strikes this hearing that if you could be at the forefront of one revolution movement, you couldn't be at the forefront of another. So Condon replied that he was not a revolutionary in physics. He raised his right hand. I believe in Archimedes' principle, formulated in the 3rd century BC. I believe in Kepler's law of motion, discovered in the 17th century. I believe in Newton's law. And he continued with a catalogue of scientists from earlier centuries. The tribunal did not appreciate humor on so grave a matter. This is from Carl Sagan's book, which I highly recommend, and Carl knew Edward well, and this is where it comes from. Now, of course, this is not new, right? There are people who stuck up for the peaceful uses, for science, for the truth, for objectivity, have always had a hard time. And here is Galileo. There he is, facing the Inquisition of the time. And he's looking a bit fed up with it all. This is very tiresome, obviously. And they're telling him that the sun goes around the earth. How can you possibly question that? Okay, so in the end, Galileo, his ideas certainly tried, and the church backed away. But this has been going on ever since the beginnings of rational thinking and science. Now, another thing Edward Condon did, which is less well known, and I didn't know it until I started preparing for this talk, is he actually built the first computer in the 20th century. That's not, usually this is attributed to John von Neumann in Princeton. But in a funny way, so the nematron, or actually nimbotron, because nim was a game that you played, a bit like noughts and crosses. But Condon was working for Westinghouse, and he designed an electronic machine to play the game. So it's called the nematron. And here you see two people playing it. This was at the World's Fair in New York. And it appeared in 1939 he displayed this machine, and apparently 50,000 people played the game. And so it's kind of amusing that the beginnings of the argument, it says up here, by the way, you can't really read it, but it says electric brain. It's kind of amusing that the origin of the computer is actually in a computer game. Condon was a bit upset that after the war, John von Neumann built a big electronic computer called ENIAC, and that led to all the stuff we have around us today. And whereas Condon was just basically playing a game, but that illustrates another side of science. Often people do things in fun, just out of curiosity or whatever, and don't actually realize they're creating the future. So, and this is a theme, as I've already said, we're drowning in information and information technology. This is the roots of it in this, in the last century at least.
What do you think a scientist's role is?
Let me play that again. So Condon clearly had one outlook on science, or maybe several, that it was fun, that it was important, needed to be shared with the world, needed to be used for peace. We're of course thrilled that just a couple of months ago, Ontario, and Waterloo in particular, gained a Nobel Prize winner, who's only the third woman ever to win the Nobel Prize in physics. The first was Marie Curie in 1903, and Marie Curie basically discovered quantum physics. It's not normally explained that way, but she did, because she saw atomic nuclei, or she saw radiation coming out of atoms, and she realized that radiation was coming from the heart of the atom. The element, the particular element that the nucleus was of, determined the type of radiation. So it's something really coming from the heart of the atom. And that radiation comes out randomly, right, in a probabilistic way. So she discovered the world is not a machine. It's not a totally predictable clock. It behaves randomly on a small scale. And that really was the seed of quantum mechanics. So that's what Marie Curie did. And then the second Nobel Prize winner was 60 years later, second female Nobel Prize, physics Nobel Prize winner, Maria Goeppert-Mayer, who discovered the shell model of the atomic nucleus, in other words, the structure of the nucleus. And then it was another 55 years before a woman won the Nobel Physics Prize, and this was done at Strickland. Now, so she won the prize for basically compressing pulses of laser light into very short, intense flashes. And that is now used in a huge range of technologies, including laser surgery and machine tools, all kinds of things. So Donna is just an amazing person. And I want to share with you a little clip from her, which shows her perspective on science and how you should, and how and why you should do science.
What do you think a scientist's role is to humanity? Is it just to discover for the sake of discovery, or do we have a responsibility as scientists to help the world? Simple question. Thank you.
Yeah, two answers to that question then. The first one is how I navigated it, and I've been told by reporters that I use the word fun a lot, but I actually think that we all should do what we find fun and what we can do. When my daughter was quite young, she was being asked by her friends about who's going out to work and rather than staying home. And my answer is the world works best if we all do what we're good at. You know, I had a nanny camp for 3 years in a nanny school in Britain, and she was much better looking after my children than I was. And I said that was the case, and she was considered the third parent in the family. And I said, I'm much better at truth and lasers, and so I should be out there in the world truth and lasers, and we should all do what we're really good at. So did I ever think, oh, I should be doing something to help humanity? No, I just think if we all do what we're really good at, it's a tough one.
Okay. So that's one point of view. And I guess that places a huge burden on all of you, because she's basically saying, I'm not good at looking after kids, so competent people should do it. And that's a very common view among physicists, is, you know, I do what I do, I sit in my corner doing what I love, and, you know, other people have to take care of the world. I'm personally afraid that that's actually not good enough, that we all need to engage more with the world, and I'll give you some examples later. But, you know, congrats to Donna. What an achievement. What an unbelievable achievement. Here is the person responsible for the information torrent we now are flooded with, Tim Berners-Lee. He invented the World Wide Web. As you probably know, this was invented at CERN, the biggest physics lab in the world. And I think one message of this talk is that physics lies at the root of most things. I'm sorry, maybe it's my blinkered perspective. But he was working at CERN, the place where Large Hadron Collider is located, and he developed the web in order to share data with scientists around the world. That was his goal. And then, of course, the whole thing grew into the internet and everything. So he says recently, this is very recent, within the last month, if you'd asked me 10 years ago, if you'd asked me 10 years ago, I would have said humanity's going to do a good job with this. Again, very, like Donna, very naive point of view, right? We just do what we're good at, and other people will take care of the world. If we connect all these people together, they're such wonderful people, they will get along. I was wrong. Okay, so I'm going to come back at the end of the talk to what Tim is trying to do about this, which is very, very interesting, and I hope you will share it with kids in school. But let's go back to the beginnings, right? Where did all this stuff come from? Where did math come from? Where did physics come from? What are its roots? Because it's clearly very powerful stuff. I mean, I call it magic that works, because it really is magic. Mathematics is magically powerful, and it actually works. Just look at everything around you. It's all a consequence of logical thinking and mathematics. This isn't widely enough known, but mathematics originated in Africa. I'm from Africa myself, and so I'd like this to be more widely appreciated, that all the early mathematical artifacts are in Africa. This is one of the earliest from the Congo, the Shango bone. It's a single bone. You see the two sides of it. There's actually a crystal of quartz embedded in one end, so you can use it to write with. It's like a little office tool, 20,000-year-old office tool. And along the edges of the bone are groups of notches. And if you count how many notches in each group, they comprise the prime numbers less than 20. Okay? And the notches on one side of the bone add up to 60, exactly. And on the other side of the bone also add up to 60, exactly. So no one quite knows what was in the mind of the person doing this, but it's pretty clear they had a fairly sophisticated notion of number, and probably they were exploring number and logic and science. So here it is, by the way. It's in an area which is now quite dangerous, the Virunga National Park, which unfortunately there are lots of armed groups roaming around and so on. Actually, the bone is in the Belgian Colonial Museum. And one of the things I would love to do is launch a campaign to take that back to Africa. It's absolutely ridiculous for this to be in Europe. Now here's another So mathematics, like all of us, came out of Africa. And this was way before early Greek science. But in Greece, these ideas sort of crystallized and became more and more powerful. So here's a very remarkable thing, which is dated. It was found in the sea. It's called the Antikythera mechanism. It was found in the sea. It looked like this when it's pulled out of the sea. And basically, it's a bronze instrument with gears and levers and all kinds of devices, which can be used to predict the eclipses of the sun and the moon to phenomenal precision. There's a wonderful video about this, and this is its title, 2,000-year-old computer decoding the Antikythera mechanism, which you can find on YouTube. And I encourage you to tell kids about this. It's really a wonderful story, how they actually understood, how they reconstructed what the original device was, and they found cleverness in its construction, which was subsequently lost. Various ways of modifying the rate of the wheels going around so that it precisely mimicked what the planets do around the sun. That's difficult. Planets go on ellipses, not circles. How do you build that into a gear? They figured out how to do that 100 BC. And people believe that this mechanism is so clever, it was probably invented around 200 BC by Archimedes. And then there were probably copies made, and this is probably one of those copies. It's really an amazing thing, and again, in a sense, it's a computer. It's an analog computer, but predicting, well, actually, why do they want to predict the eclipses? That's because they felt the eclipses were signals from the gods, right? And when these eclipses happened, they had dramatic effects on human society. This was a statement from the heavens that we were on the wrong track, okay? And threatening to turn the lights off, right? And so the kings in particular really wanted to know when is the next eclipse, because that may be the end of them. So there were mystical, very powerful mystical reasons why this information is incredibly important to early Greek society. Now, this was the rise of science in ancient Greece. Unfortunately, the African period, we just don't have data. But in ancient Greece, you can plot the number of natural and so there were about 61 natural philosophers. That's what they were called at the time. These are people who believed in learning from nature, learning from the universe in particular. The origin of Greek science is all about learning from the stars. Longer. The natural philosophers sort of died out, followed by the rise of Islamic science. And so these are people who, and then medieval scientists, people like Roger Bacon and Gutenberg, who invented the printing press, and so on. So these are the early people ending in Copernicus, which marks the beginning of the Renaissance and modern science, and Galileo, of course. So I think the message from this picture is, science can come and go. Be careful. This ancient wisdom and knowledge is a fragile thing, and it's been destroyed many times. Okay? Science doesn't necessarily survive. We have to treasure it and protect it. So now we're going to do a little bit of mathematics. I want to go back to Pythagoras, one of the very first. By the way, Pythagoras in his life illustrates that principle. So Pythagoreans believed they had access to mystical knowledge. Mathematics was the most powerful mystical knowledge. Pythagoras, for some reason, he realized that music is mathematical. Okay, harmonies are mathematical, and he understood that. And he then said, well, if that's mathematical, maybe the heavens are mathematical, because they're also pretty beautiful. Okay, so he thought these things went together, that mathematics was sort of the explanation of beauty and harmony in the world. But he kept his knowledge secret, didn't believe in sharing it, formed a secret society, and then from time to time the local town would come to them for advice. How do we plan the roads? How do we build our buildings? And the Pythagoreans would give them their suggestions, and this was very valuable. But over time the resentment grew. Said, you guys, you're superior. You believe you're superior to us. And eventually they came and burned down Pythagoras' temple or community, and he was, according to myth, murdered. And so that's one of the dangers, again. Don't challenge science. But anyway, Pythagoras came up with this mathematical proof, very beautiful, of the sum of squares. The squares of the lengths of the edges of a right-angled triangle. So I want to explain the proof to you. There's many proofs of it, but there's one particularly nice one that I like. So take this triangle, right-angled triangle, and draw a perpendicular from the longest edge to the opposite corner, right, the black line. Now you should be able to see three triangles as soon as you do that, right? There's this little one, there's the bigger one, and there's the original one. And if you look carefully at this, you'll notice they're actually identical, but just scaled up and down, right? So why are they identical? Well, clearly this angle is the same, it is between this triangle and the bigger one. They have the same angle. They also have one side the same, but it happens to be the biggest side of this triangle, where it's the middle side, length side of the bigger triangle, and so on. If you stare at this picture, you will convince yourself that these triangles are all just scaled up and down versions of the same thing. Now then you ask, well, what is their area? So an area is the square of a length. And so if I just take an object, any shape at all, and scale up its length by some amount, the area scales like the square. Okay, again, that's intuitive. And so, but clearly, the two smaller triangles, the sum of their areas is the area of the bigger triangle. Right? Now, since area is proportional to the square of the length, it follows that the sum of these two length squares must equal the length square of that, because they're both the longest side of their triangle. So the square must be equal. So that's it. This simple statement about geometry underlies all of modern physics. It's really incredible. It underlies general relativity, it underlies quantum mechanics. I'm not going to explain all of that, but I'm going to give you a little taste of quantum mechanics. And again, apologies for the brain exercise. It's a very magic number called pi. Okay? And this was actually discovered in the Middle Ages. But there is a number whose square is -1. And so, of course, that makes no sense at all. How can I write a triangle whose area is negative? What people discovered, and again, it was done in a secretive way, people used to hold maths competitions in the Middle Ages in Italy. And there were big rewards. You could win a bag of gold if you solved an equation faster than anyone else. So the person who discovered this number, or invented it, realized that using this number, he could solve those equations faster than anyone else. But he didn't reveal his secret because it was too valuable. Okay? And then there was a big fight about priority and who had invented it and so on. But it was extremely valuable. It sounds crazy, the number whose square is -1, but it's incredibly useful. But the real person who took this to exponential heights literally, was Leonard Euler, one of the most brilliant mathematicians of all time. And the word exponential is actually E, comes from E, the number E, and that's Euler. Is getting old, and apparently managed to do all this mathematics and even write the papers about it. Literally, hundreds and hundreds of papers while he was old and blind. Amazing person. He realized this formula. Now let me explain a little bit about that. So here you see the exponential. Where does the idea of an exponential come from? It comes from exponential growth, and so that goes up. The increase is proportional to how much you have. And that just continues in there, in the exponents. I'm growing exponentially, but in an imaginary direction. This is called the imaginary number. So then he discovered that actually you get trigonometry. Out of that formula, you get cosines and sines, and they come in as well. So with this, of course, it wasn't invented until the 20th century. So it's a wonderful story. Now, I'll try to convey a little bit about how that happens. So let's take a triangle whose long edge is 1. Okay, so it follows from Pythagoras that the sum of the squares of these two sides must be 1. And this is the definition of the cosine. It's the ratio of the side next to the angle to the hypotenuse, and the sine is the ratio of the side opposite the angle to the hypotenuse. So there's a very neat way of getting something which adds up to 1. If I change the angle, right? So if I have this round in a circle, the sum of the squares is always going to be 1. So rather than getting exponential growth, you're going to get a description of something that goes back and forth, like round and round. And that's very useful, because basically things in nature either go round and round, or they go up. Okay? At a first approximation, right? The Earth, the planets go around the sun, they don't blow up. But, occasionally you do something dramatic and things go up for a while. So these are the two kind of fundamental behaviors in nature. And this is a good way of describing things that go round and round. But here they are going round and round. So we have the circle, and the point of the circle goes round and round. And if you keep track of the height of that point, it will trace out a beautiful sinusoidal wave. And so when people study, for example, AC, alternating currents in electricity, they use this technique. They use the number R, and that describes the oscillation of the current. Likewise, when we discuss waves, like light waves or radio waves, we describe them by having this point going around and around in a circle that tells you how the electric or magnetic fields vary in the wave. But even more interesting, you can use it for probability. So if you think physics is not deterministic, it's not a machine, but it spits out probabilities, this is an amazing way of making sure your probabilities make sense. So you imagine, so this is for just a circle, but we could go to higher dimensions. We could have any number of dimensions, so Pythagoras is still true. So basically imagine this big sphere, and a pointer of the sphere, and it goes round and round and round like this. But the sum of the squares is always 1. Then what you do is assign probabilities according to the length squared in any particular direction. And that will tell you the probability of any particular outcome. And you're guaranteed it always adds up to 1. So this is basically the mathematical trick behind quantum mechanics. So let's see an example of this. So here is a light source emitting this fuzzy green stuff, which nobody has ever seen, by the way. Okay. But that's the quantum description of photons. The fuzzy green stuff, which we can't see, travels through a double slit and eventually encounters a screen where it lands. And notice when it lands, you see these 3 fuzzballs. When they land, there's a point appears somewhere. Okay? So three possibilities for where the particle goes, but it chooses one in a probabilistic way. Okay, so if you notice, we never see the green fuzz. What we see are the photons, the particles of light. You see flashes of light. So how they travel is in this, what we call a possibility wave, and how they land or become visible is as particles, not as a wave. It's called the wave-particle duality. So one way of saying it is that things are kind of imaginary in this phase. This eye is crucial in the description, but we can never see the eye. Okay, we only see things land and become definite, and when they do that, we have to use probability. Now, the wonderful thing about this is that most likely the universe is explained by this phenomenon, and we'll come to that. This is really very, very fundamental. It's not just tiny things that are quantum. The whole universe is very likely quantum. So I want to say a little bit about myself. Excuse me. I was your worst nightmare at school. A very, very naughty child with big ears, very aggressive, and very unhappy. And the reason I was so unhappy, I was in South Africa, but my parents were both political activists. Here's my mom giving a speech, and here's my dad. He's sitting in this row, and over there is Nelson Mandela. Okay, so and there he was in the treason trial. Actually, they all got off, but then the government just changed the law so that they could put everyone in jail without justification. And so this is my background. So yes, I was an odd kid, a troublesome kid, difficult kid. We then left South Africa. We lived in East Africa, and then we went to the UK, where I went to school. And I was always the odd one out. And so I want to give you a little quote about that. The importance of people who are different, unusual, and difficult, and how one shouldn't discard such people. So I'm going to show you Jocelyn Bell Linnell. She's another spectacular physicist who was awarded the biggest prize in science this year. It's called the Special Breakthrough Prize in Physics. She was awarded it for a discovery she made in the 60s of neutron stars. It's probably the most spectacular discovery ever made, certainly in 20th century astronomy. So amazing discovery, made as a graduate student. By the way, Donna Strickland also made her big discovery as a graduate student. So they share a history, and we were lucky to have them last month at Brimley, both of them. We had a celebration of their prizes, which are quite special. And Donna has a Jocelyn has a slightly different perspective than Donna.
I recognize now that I was suffering from imposter syndrome. I came from this north and west uncouth part of the country, turned up in this very suave Cambridge. And I thought, they're all terribly bright here. They've made a mistake. They're going to discover their mistake. But I'm a bit of a fighter. So I said, I will work my very hardest until they throw me out. So that when they throw me out, I won't have a guilty conscience. I know I've done my best, and I just wasn't bright enough for Cambridge.
So, of course, she did this spectacular work, which earned a Nobel Prize for her advisor in the 70s, and then she was kind of overlooked for decades, and finally recognized with this Breakthrough Prize. Now, the Special Breakthrough Prize is a big prize, $3 million. Guess what she did with it? You see what kind of person she is. So she gave the whole prize to create PhD fellowships. Again, talk a little bit about me. This was my teacher. You notice there are two of them. Okay. So this was my science teacher at school, Margaret Carney. I had her as a teacher in Tanzania, but she's a Scot. She was a volunteer working in Africa. And she lived with her identical twin sister, Anne, and their mother. The three of them lived together. They were all school teachers and utterly devoted. They lived in a flat on top of the school. And she's really the one who got me interested in science. Because all day we would just do experiments and go outside and make maps of the school. And there was never any prescribed curriculum. In fact, it was quite amazing because the school, I was a primary school student, right? So I was eight and 9 years old. The school created a common room for the more advanced students so that we could go and enjoy our breaks and have discussions in our common. It's quite incredible. So they treated us with enormous, as if we were enormously mature. And it was just a government school. This is not a special school in any way. Around a bit with this photo. It's hard, it's really hard to tell who is who. Yes, and Margaret was, they're both amazing people. And Stephen Hawking, I talked to him about him before. Stephen also attributes his interest in science to his teacher. Here's Stephen, a gawky public school boy. And here's his teacher, Vikram Tata, who was an Armenian refugee. By the way, don't neglect refugees. You neglect refugees at your peril. And here they are making, guess what? An electronic computer. Right? So Stephen says his whole interest in mathematics and science came about because of Mr. Tata. And Stephen has a lovely quote that he said, behind every exceptional person, you will find an exceptional teacher. So that, and of course, this is my passion.